you know that the new lab will take place in a different room. Not 134, but 136. Well, now I can say good morning. Good morning. The issue is, officially this is on-site course, not blended, not online. So I have to take attendance. You have to be here, even if we may not like it or not need it. So people who are not here, they don't know that the lab will be in a different room. So should I send an email and inform them, or should I let them just wander around? And you tell me, what do you think should I do? Anybody? What would you do in my place? Yes? Okay. I will. You're too nice. Physics, yes?
In the lab on Monday, there was a sign saying the lab today was, but it's definitely in room 136, right?
138, the room doesn't exist.
Okay.
It's 134, our regular room, and the next one is 136. And 138, it's an elevator, probably. That's probably, yeah, teaching fella made a mistake. All right, so that's a question. Please make your mind. Enter your answer. Of course, the best approach would be actually drawing your own picture, because that would make your brain be more active, because watching and listening doesn't really help learning. That's an urban myth. Learning comes through actions. You know, when someone drives to work and back home every day, it doesn't make that someone professional driver. Someone who cooks every day to eat doesn't make it professional chef. So someone who reads slides to students every day doesn't necessarily a professional teacher. I am a professional teacher. So if I advise you to act, that's based on long and successful experience. You don't have to follow my advice. I cannot force you. But I strongly advise to draw your own picture. And follow the steps for drawing the lever arm. This picture is very helpful. It gives you many, many options, but you can pretend you don't see it and do your own. And draw your own lever arm, and then you can compare your picture with a set of answers provided to you, make a selection, enter it. I'm pretty sure it's going to be the right one. So strictly speaking, all we need is a force and the axis of rotation, nothing else. The force in the question is the tension, and the axis is in the hinge. We saw this device yesterday. So step number 1 requires extending the vector of the force to draw the line of action. And step number 2 requires what? Someone has to tell me what to do, and I will do it. Don't tell me leave the room. That's actually an additional action. Putting words together and then pronouncing those words makes learning even more effective. Yes? Like this? All right, sorry. I just like writing these words, so because it helps learning. Like this? Exactly. From the axis of rotation to the line of action using shortest path, which is perpendicular to the line. That's the lever arm of the force of tension. So now you can pick, what number did you pick for the answer? The lever arm is represented by the segment number. But it doesn't look like 90 degrees angle. This looks better to me. And I can understand that picture might be a little bit skewed. But from my perspective, I would choose 3. But if you chose 4 or 2, close enough, 7 is definitely wrong. Well, there's a Russian saying, a morning is wiser than the evening. It definitely was for me today. When I was cleaning my teeth, I saw this slide in my mind and I realized I want to change it. You still need to draw the free body diagram, copy the picture, but I'm going to add some extra elements. So in this case, we use, well, it's like, lamp stand. You can have a lamp hanging down, and to hold it at a certain angle, you use a string, which more or less horizontal here. And since we have manufactured this device, we know how heavy this rod is, we know the length of this rod, and we need to calculate force of tension or contact force because we need to know what string would we have to use so it wouldn't break. Different material have different critical strength, as we saw in the past. So this is my favorite part of every class. You work, I rest. You have to solve this problem By the way, we hadn't had a discussion yet. What is a problem? We say it every day. I have a problem, we have a problem. Do you have a problem? We have to solve a problem. What does this word actually mean? Right now, are you solving a problem? What do you think? What is a problem? We say this word every day probably. But what do we really mean by that? Have you used this word in your life? Have you ever said problem? What did you mean? Something wrong. Well, probably if it's wrong but you don't care, that wouldn't be a problem, right? So it's something which feels wrong, but on the other hand, you kind of want to fix it. Otherwise, why would you even bother? However, that's not always just that. Sometimes you don't really have to think about what to do. Yeah? You enter your room, it's dark, it's a problem, you know what to do, you know where the switch is. You just reach out, flip it on, and that's it. So that's not really a problem, right? Bless you. Well, the elements of a problem. First of all, of course, a goal. We have a goal to achieve, but even if it's a very complicated goal, requires complicated actions, if we know what to do, we just do it. So it's not really a problem. It's a task. You just have to fulfill it, finish it, done. A problem, in its essence, is a situation when we have to achieve a goal, when we have to do something, but we don't know what to do. That's a problem. In physics, it happens when we have to create a solution, not just copy a solution of something we've done before. Is it a problem? I don't know. For some of you, it might be a task because you know the strategy. You just have to follow it step by step. Step number 1, draw a picture. Step number 2, convert it into a diagram because you have to add forces acting on the object of your choice. Step number 3, choose the axis of rotation and show it clearly and explicitly. Step number 4, calculate the torque for each individual force acting on this object relative to the axis of your choice. Step number 5, set the torque balance equation. After that, you can write physics is done. But if you don't know the strategy, that's not going to be a task for you. That's going to be a problem. And you will have to create right here, right now, create the solution from scratch. And that, of course, is much, much more difficult work to do. That's why learning strategies is an important part of a learning process. In that case, you don't have to invent things. You can just find the thing which have been invented, proved workable, proved usable, and apply it. Anybody who feels like showing off, can do it right here on the board in front of the whole class. Feel free. There is a rule of thumb. If you don't know, well, this is not an actual board. But if we had an actual blackboard with a chalk, you know, they talk to you. You see it, you don't hear it. But if you're right here, it tells you what to do. Well, right now we have a touch screen. It doesn't talk as nice as the board used to, but still. If you're not sure what to do, go ahead. I can give you a pen, the screen, and immediately you will know what to do. Or you can ask a question, which could help you. So if it's a task, that means you know the steps, you just follow the steps. If it's a problem, that means you're not sure what to do. If you're not sure what to do, there is a specific action which always helps you to make a step ahead. That action has a name, asking. You have to ask a question. That question, of course, should be specific. You can't ask how to solve this problem. You have to ask a question like how to calculate force of gravity. That's a specific question about specific calculation. Or how to draw a lever arm. That's a specific question about specific action. Anything specific which would help you to propel your reasoning from the beginning of the creating your solution to creating your solution. Forces should act on the object of your choice. And I see that your object is a rod. So for the rod, how many forces act on it? So 2, maybe 3, and we always have a rule which tells us how to check our hypothesis. Every force has a source. If you draw an arrow which represents a force, you should be able to point a finger at an object which is responsible for creation, for the existence of that force. So, for example, you say 2. All right. Could you please name one of those forces? Tension, because it's created by the string. They touch each other. Touching means interacting. Perfect. What else? Gravity, yes, because the Earth always pulls everything down. It exists. So there's a force of gravity, 2 forces. By the way, for a uniform rod, the force of gravity is applied to which point? Center of mass, which is where for this rod? In the middle. Yeah. So the force of gravity should be applied to the middle of it. Now, is there anything else touching the rod? Does it touch it? Do they feel each other? Yes. Touching means interacting. Interacting means the force. So that's the force number 3. Can you name any other objects, actual physical objects, which interact with this green rod? Anybody? Can you name any other, besides string, earth, and wall or hinge, any other object which interacts with the rod? Can you? I'll say yes or no question. Yes, we can. Name it. No, we can't. In that case, we're done. So, can you? Are we done? Done. Me too. I don't see anything else which would touch it. We could have attach a lamp or something else, but in this situation, nothing else except this string. The earth, and the hinge, the wall, exert any forces, only 3 forces. Okay, step 1, step 2, step 3, axis. Where do you want to choose the axis? By now, everybody should already have the axis set somewhere. The axis is a dot with a 0 or a capital A or capital O nearby, which tells origin or axis. So to choose the axis, you have to act. It's not in your mind. You take your pen, you draw a dot, you write O. Yes? Exactly, because I don't know. I have to choose the most general direction. I have no idea. Maybe it is horizontal. Maybe it is vertical. But I don't know. So my guess must be the most general one. And if my further calculation tells me that horizontal component equals 0, well, it will be equal to 0. If my further calculation would tell me that vertical component equals 0, well, so it doesn't have vertical component, but I don't know. So I cannot constrain myself by making a specific selection. I have to make a general assumption. But I thought you would want to tell me where to choose the axis. So now you have to tell me where to choose the axis. At the hinge. As you know very well, because it's her words, that's her fault. At the hinge. Why do you think that would be the most convenient choice? Absolutely right. The contact force seems like the most complicated one. And we cannot eliminate the force, but we know when we want to calculate torque, if force has no lever arm, no distance from the axis to the line of action, torque of that force will become equal to 0. And the more zeros we have, the better. So now, next step, we have to start writing torque number 1, torque number 2, torque number 3. So I'm going to call them force number 1, force number 2, force number 3, torque number 1, torque number 2, torque number 3. For each torque, we have to make a statement about magnitude and direction. So torque number 1, what number should I write? For the torque of the contact force relative to the axis chosen at the hinge. Number? Number. Just tell me a number, any. Pi, -7, square root of 5. Yes, you moved. I saw it. Please tell me a number which represents the magnitude of the torque generated by this force about this axis. You're asking? 0. It is 0. We've done it before several times. There is no distance from the axis to the line of action or to the point of application. So it's 0 times force, 0 torque. Torque number 2 is generated by tension. And about the axis of our choice, would it be positive or negative torque? What do you think? Tension points horizontally to the left. So in order to answer that question, first we have to say, would it move this rod? If nothing else would be acting, would it move this rod counterclockwise or clockwise? That's not physics. That's common sense and everyday experience. Right now, the rod is in equilibrium, but what if we start pulling stronger on the string? The equilibrium would have been broken, and the rod would start moving. How? Counterclockwise or clockwise? Counterclockwise, which makes it positive. Well, again, this is how we could look at it. That's the force in the question. That's the axis. We can always imagine that the line of action actually is a part of a large circle. So we can bend a little bit, pretending there is a circle like this with the axis inside. And now we can see that this type of a circle would look counterclockwise for us. Now, how do we write the magnitude of this torque, which should multiply tension times the lever arm of the force of tension? There are two more expressions you can use, but it's up to you. I like this one. And the torque number 3 is due to force of gravity. And that's got to be negative because it's clockwise. Plus, if we have one positive torque and one zero, we must have one negative. They have to cancel each other. So that should be equal to magnitude of the force times lever arm of the force of gravity. And that's actually equal to a certain number, 0.5 kilograms times 10 meters per second squared times the lever arm of the force of gravity, which gives us 5 times L. Well, now we're going to back to the slide number 1. The question about finding a lever arm. We have answered that question, and we know what to do. So please do it. You need to write 2 numbers, actual numbers, 1 number for the lever arm of the tension force about that axis, and eventually 2nd number for the lever arm of the force of gravity about the same axis. Those are numbers. After doing that, finally we can write the torque balance equation. Torque number 1 plus torque number 2 plus torque number 3 equals 0. And when I write this, I mean components, not magnitudes. So 0 plus force of tension times the lever arm, which you should find. And technically, I should write a plus. -5 times the lever arm of the force of gravity. That should be equal to 0. Now I can solve this equation immediately for the force of tension. Force of tension will be equal to 5 times the lever arm of the force of gravity divided by the lever arm of the force of tension. And since these numbers come from picture, you plug these numbers in and you solve the first part of this problem. So please just tell me, and then we will check. Anybody, please tell me your number for the lever arm of the force of tension. in order to make me move ahead, you have to say a number. Any number will do, but you have to say a number. Someone has to say a number. Please repeat, I couldn't hear you. Zero 0.02. 0.20. I want to insert the slide. You see it, right? Yeah. So we just need, again, a clear picture. So the length of this rod L is equal to 40 centimeters or 0.2 meters. Actually, can keep centimeters because it's L over L, unit cancels. And the line of action of the force of tension is a horizontal line which crosses the wall above the hinge. And according to a definition of the lever arm, it has to be equal to the distance from the axis of rotation, shortest distance to the line of action, this perpendicular. And in the picture it was called H. And now we have to do the geometry. Since this angle was given as 30 degrees, that means this angle equals 30 degrees. So H, which is the lever arm of the force of tension, will be equal to hypotenuse times sine of 30, which is 0.4 times 1/2, 0.2. And now we can use the same picture for the lever arm of the force of gravity. Force of gravity is applied to the middle point of this rod. And what we have to do, we have to extend the force vector. Then we have to draw the shortest segment for the axis of rotation toward the line of action. And look at it. Normally we search for a right triangle and we see it. This triangle has the hypotenuse which equals 1/2 of the length of the rod. This angle equals 30 degrees, but the lever arm is a horizontal segment. So the geometry tells us we have to multiply the hypotenuse times cosine of this angle, wherever it is. So 0.2 times cosine of 30, 0.17. But actually I prefer keep it as 0.2 times cosine of 30. Why? Because I can see 0.2 and 0.2, they will cancel each other. So the force of tension will be equal to 5 times the lever arm of the gravity over the lever arm of the tension, 0.2 times cosine 30 over 0.2 and 5. 5 times cosine 30 newtons. Now this is a situation when the force balance equation helps faster for calculating the components of the contact force. So if we look at the force diagram, that's the contact force. There is a force of gravity. There is a force of tension. And the sum of these forces have to be equal to 0. Which immediately tells us that the horizontal component of the contact force plus horizontal force, which is tension, should be equal to 0. So the horizontal component of the contact force should have the same magnitude of force of tension which is 5 times cosine 30. So we've done with the x-axis. And immediately we can see that the vertical component of the contact force plus force of gravity should be equal to 0. So the vertical component of the contact force is not 0, but it equals to mg, which is 5 newtons. So this force has 2 components. How does it point? Well, something like this. It must have 2 components. The x component of the contact force points to the right. The y component of the contact force points up. We can calculate at which angle from the wall it points. And of course, we can calculate the magnitude. We just have to apply now the Pythagorean theorem. The contact force as the magnitude equals square root of sum of the squares. And we are done with this problem. Well, any questions? This is probably the final illustration of this strategy. I planned to spend 7 minutes on the diagram, and I spent 35 minutes instead for the whole problem. Which means now I'm going to start speaking much faster. It's the law of conservation of speed of speech. All right. We said that a special point called center of gravity is that point where force of gravity is being applied to an object. That's an official definition. Now the question is, how do we find it? Well, there are several options. Number one, technical, experimental, actually physical. So, well, if I start from a uniform object, if I try to hold it anywhere from the middle, it's not going to be in equilibrium. And the only reason for that, force of gravity. If the force of gravity would be acting here, gravity and normal would cancel each other, plus torque of gravity and torque of normal would cancel each other, and the object should have been in equilibrium. But it's not, which means force of gravity is not applied here. It's applied somewhere to the right, to this, well, to the left for you, to this point, because that's how it makes it move. So what can I do? I can try to shift my finger until I find a location of the equilibrium. Done. It's in equilibrium, which means force of gravity and well, normal force cancel each other out, and the torque of gravity and torque of normal also cancel each other out. And that only can happen if gravity is applied here, because if it would have been applied here, that would make it move. And if it's not a uniform object, I can do the same kind of search, find the location where I can hold it, and the object remains in equilibrium. Somewhere here, close enough. But of course, there is a physics behind that. The physics has been described in words. Now we have to describe it in a picture and in equation. So let's say we have some kind of object. Let's say we make an assumption that the force of gravity is here, the center of gravity is here. So the force of gravity should be acting there. If I would hold my object at a different location relative to the natural choice of this axis, the torque acting from gravity would not be equal to 0. The object would start rotating So the location of that point, which I use as a suspension point, and the object remains in equilibrium, that location is the location of the center of gravity. Because now, not just net force equals 0, but also net torque acting on this object also will be equal to 0. Now, we have to convert it into some kind of a calculation. So let's pretend that this is not a baseball bat, but this is actually a uniform rod with an attachment at the end. So a uniform rod has the center of gravity right in the middle, but if we attach something, it shifts the center of gravity toward the heavier end, like in this situation, toward here. Come on. Yes. But we have to calculate it. We have to find that distance, yeah? So what would we do? Well, of course, we select the point where we think the center of gravity is located. And we know it's supposed to be closer to the heavy end. And we draw mg, and we draw that suspension, F tension or normal. But this doesn't help at all. It only tells, yes, it's not moving, it's in equilibrium. Everything cancels each other out. So what do? It's a system composed of several objects, 1, 2. And for each object, there is a force of gravity acting on that object. So for example, there is a force of gravity acting on this additional weight, and that's supposed to be applied to the middle point of this weight, and we say it's very small. So also, there is a force of gravity acting on the meter stick only. And that force of gravity is supposed to be acting on the meter stick and applied to the middle of meter stick. But the action of two forces on the right and the action of one force on the left, this is the mass of the system. This is the mass of the weight. This is the mass of the meter stick. So these two forces together should provide the same action as this one force. But in that situation on the right, we know what to do. So still the same suspension point. We can choose the axis at the center of gravity right here. And because the net torque has to be equal to 0, well, we can set an equation. This is the distance we are looking for. The distance, let's say, from the left end to the location of the center of gravity is an unknown. So on one hand, the counterclockwise torque from the weight acts on this system. On another hand, the clockwise torque from the force of gravity acting on the meter stick is acting on it. And those two torques must cancel each other out. They must have the same magnitude. So what do we have? We can cancel gravity. This is this is 200 grams times x, and that should be equal to 100 grams times 1/2 minus x. Why 1/2 minus x? Because this is 1/2 of a meter. So this is the lever arm of the force of gravity relative to the axis. Well, I can cancel two zeros on the left and the right. 2x equals 1/2 minus x, 3x equals 1/2, x equals 1/6 of a meter. So for this particular example, the center of gravity will be located 1/6 of a meter stick from the left end, from the heavy one. If we suspend this system at that point, it will remain in equilibrium, will not spin, will not rotate in any direction. Well, so now you can read it. Is center of gravity and center of mass same thing? To answer this question, we have to calculate the center of mass and see if it's located at the same point. So how would we calculate the center of mass? We know that because we did lap number 6. So this system is an equivalent of, well, something which has a mass of 200 grams and something else which has the mass of 100 grams, located at 1/2 of a meter from each other. Where is the center of mass of this system? Well, we know that in general the equation for the center of mass tells us to do this. x1 m1 plus x2 m2 divided by m1 plus m2. To apply this equation, we need to draw the x-axis, choose the origin somewhere to the most left, and now apply the equation. So it gives me 0 times 200, and I use grams, plus 1/2 times 100 divided by 200 plus 100. And believe me or not, that's 1/6. Zeros getting cancelled. 1/2 over 3, 1/6. Exactly same number. So, yes. But from historical reason, people sometimes keep naming center of mass as center of gravity, even if it's kind of outdated. What do we do if the object is not one-dimensional but two-dimensional, like something like this? Well, again, we have an option, just try to find that point where we can hold it and keep it in equilibrium. That's supposed to be the center of gravity or center of mass, here, here. But there is another more accurate way. Oops, okay. If I let it go, it rotates, but eventually it brought in equilibrium. And that means the force of gravity acting on this shape has to act straight down and has to be applied somewhere on this line. Maybe here, maybe here, maybe here, maybe here. We don't know yet where, but on this line, because otherwise the torque would not be compensated and it would spin. So how can we see the line? Just have to use a plumb bob. Who stole my chalk? No. Before the class, I placed a piece of chalk on my cart. Now it's gone. Too late. Thank you. So we just have to draw this line. The center of gravity, center of mass is somewhere on this line. Too many points. What do? We just draw a second line, because now the same center of gravity should be somewhere on this line. There's only one intersection, and that is the center of mass or center of gravity. And I can prove it by hypnotizing this. Stay. It's not physics, it's mind. Well, so this is how it's done. And one more example related to equilibrium, which is important for us because we live in buildings and we don't want them to fall. Every building has a center of mass, and the force of gravity acting on the center of mass points down. But in this situation, the normal force acting from the surface on the base cancels force and torque, so nothing bad yet happening. If I add some more stores, that shifts the center of mass higher, and now the force of gravity will missing the base, so the torque from the base will not be able to compensate the torque from gravity. Falls. I'm just going to draw these two pictures. So situation number one, something like this. Center of gravity, or center of mass, whatever you call it. So, and to compensate, the normal force can cancel it out and can cancel out the torque. But if the center of mass now in such a place, so the force of gravity has the line of action beyond the base, that's it. Cannot be canceled, starts falling. Well, of course, we could add some, extra devices to hold it, like they do in Pisa. But it still keeps leaning, so eventually, probably, it will fall. And if you know the history, Galileo was dropping balls from this tower to prove that mass doesn't affect how objects fall. Well, and last example, something about medicine. Don't read this slide. It's just an example how mechanics can help physiology, medicine. So we know that muscles exert certain forces, and we can actually calculate, make an estimation for the magnitude of a force acting on a tailbone when a person tries to lift a weight. We just have to apply torque balance equation, and turns out the force which compresses or the spine is rather large. It's an equivalent of, in this calculation, 170 kilograms. But that happens when you try to use your back. So you can break your back by doing that. That's why common sense and folk wisdom tells us don't use your back, use your legs. Physics. Well, now we're going to start talking about situation when net torque is not equal to 0. Net force still is 0, like in this example. Forces have the same magnitude in opposite direction, but torque is not 0 anymore, and we observe rotational motion. We know how to describe it. We just have to apply the Newton's second law for rotation. Net torque is equal to a product of two variables. One variable represents the inertial properties of a system. We call it the moment of inertia or rotational inertia. It tells us how hard or how easy to make it spin about a certain axis. And the second variable is angular acceleration. So moment of inertia, rotational inertia, depends on the mass distribution, depends on the shape. This is an example. If we have a disk, and we have an attachment to that disk, and we want to calculate the moment of inertia of that system. If I only had a disk, the moment of inertia relative to the axis which goes through the middle point would be equal to 1/2 times mass times radius squared. But if I add a relatively small in size, so we can treat it as a point object, that will change the inertial properties of the whole system. So how would we calculate the new moment of inertia? That's actually a very trivial calculation. You just have to add two individual moments of inertia. So for the system, we have to add the moment of inertia of a cylinder or a disk plus the moment of inertia of that mass. The name tells us what equation should we use for each individual term. For the cylinder, for the disk, it's 1/2 times the mass of the disk times the radius squared. And for the individual small mass, it's, it's the mass of that additional object times the distance from the axis to the object. But in this situation, this distance and the radius are equal to each other, so same r squared. Well, now we just have to plug in numbers. 1/2. I have to use kilograms, so 0.2 and the radius 0.2 squared plus the mass of the object 50 grams, so 0.05 times same radius 0.2 squared. What will be the unit of it? Mass times radius squared tells us the unit will be a kilogram times a meter squared. And this combination of basic units has no name, just kilogram times meter squared. That's it. So wherever it is, that's the number. Question. How does shifting mass affect the inertia? In this situation, I start from two masses located like at 1/3 of the rod. I can actually feel how easy or how hard to make it spin. And I want to move them in such a way so inertia would increase. Well, how can I move them? Closer to the axis or farther away. And when I do that, I change the inertial properties of it. So question number one, by moving the masses along the rod, question to you. Did I change the mass of this rod? Did I change the mass of this weight? Did I change the mass of the whole system? No. So we didn't change the mass. What we did change is mass distribution. We distributed mass differently. That's what it is about. By the way, here I have an example. Anybody who's curious enough can play with this right now or anytime. Two absolutely seemingly identical rods, same mass, but if you try to spin them, you can feel the difference. It's much easier to spin this one than this one. Same mass, what should be different? Mass distribution. So inside this rod, the same mass should be shifted. And the question is how? Well, first of all, our intuition tells us away. But mathematics also tells us that if we want to increase the inertia, we have to do this. That the inertia of the whole system, the rotational inertia of the whole system, will be equal to 12m times L squared plus m1 r1 squared plus m2 r2 squared. And the first term remains constant in this example, but by shifting, moving the weights in a certain direction, we affect the inertia. Yeah. From this equation, if R1 and R2 both increase, that leads to the increase in inertia of the whole system. Just pure math. Well, I want you to answer this question. What do you think? In this case, we have two different objects which have the same size and the same mass, sphere and disc or cylinder, it doesn't matter. Initially, both are at rest. And we apply exactly the same torque to both. We wait 1 second. Question is, in 1 second, which is going to spin faster? If you think the sphere, choose 1. If you think the cylinder, choose 2. They might spin equally fast, so choose 3. The equation which we need to use someone made it red, but you don't know, maybe it's a wrong answer. The equation which we need to use is on the screen, because what does it mean spins fast? It means we need to say something about angular velocity. But angular velocity is related to angular acceleration, and angular acceleration is related to torque and inertia. How? Well, more inertia, lower acceleration, assuming the torque is the same, which is the case in this problem. Now, less acceleration, but same time, means final velocity will be lower. So more inertia leads to lower velocity. And which of these two objects has a lower, what did you say? High inertia, higher inertia. Yeah, the error was correct. Higher inertia leads to a lower velocity, which actually just a mirror of the relationship between mass and velocity we had before. More inertia means harder to change the state of this system. So over same time, the state will not be changed as much. So in this situation, more inertia, which of these two objects has more inertia, has less inertia? Since they both have the same mass, since they both have the same size. The answer is in the coefficient. This coefficient actually has a name, form factor, because it depends on the form. It's a factor of a form. And in general, any rotational inertia can be written as some kind of a coefficient, the form factor of that object, times the mass of that object, times size squared. The size is usually a radius of the length. So a cylinder has form factor of 1/2, and a sphere has form factor of a 2/5. So what is greater, 1/2 or 2/5? That's basically the question. 1/2 versus 2/5. When we need to compare two numbers, we always have to choose one answer from 3 possible answers. 2 are wrong, 1 is correct. So what should I choose? The top, the middle, or the bottom? You sure? What do you say? How do you prove it? That's absolutely right. The easiest way, converted, this is 0.5, this is 0.4. That's the easiest way. There's another way. You can, if you need to compare two numbers, you can divide them. This divided by that, if the result is greater than 1. You can subtract them. This minus this, if the result is greater than 0, it gives you the answer. So in this situation, 1/2 is greater than 2/5. So the cylinder is more inertial, sphere is less inertial. So in the same time, it reaches faster, higher speed. So this is basically problem from arithmetics. All right, now we're going to start applying the Newton's second law of rotational motion. First example, we have a disk. We have a string wound up. We pull on a string. Instead of a string, I could apply a finger force to make it spin. As long as we know the shape, the mass, and the force, we can calculate acceleration. If we know acceleration and time, we can calculate velocity. We can calculate displacement. So, why is it important to know the name of the object? That's why. The form factor depends on the shape of the object. It's disk or cylinder. The inertia equals 1/2 times mass times radius squared. Would have been a sphere, would have been different form factor. Now, well, since we have to use torque, we have to select the axis. And of course, in a case like this, the actual physical axis is the best choice. It will spin about that axle, and the force of tension responsible for the torque, which makes it spin. So if you want to, and in real life situation, there is of course force of gravity, and normal force could have been friction. If we couldn't neglect friction, how would it affect? Well, it would try slow it down. So we know from our everyday experience that if we pull on this string like this, the direction of rotation will be, how do we call that direction? Clockwise, which means angular velocity points clockwise, and angular acceleration, because it's speeding up, angular velocity, angular acceleration. But as we know very well, friction always opposes the motion. So friction would generate a torque in opposite to velocity. This would have been torque of friction. We will solve a problem like that in the future, but right now we neglect friction. So if we look at this picture relative to this axis, no friction, there is only one torque responsible for acceleration, torque of the force of tension. If there is only one torque, that's one torque is the net torque. So it's just easier to use magnitudes for everything. And what can we write? Torque will be equal to force times radius, because this distance represents radius and the lever arm at the same time. And that should be equal to 1/2 times mass times radius squared times the angular acceleration. And what are we looking for? Tension. That will be equal to 1/2 times mass radius squared acceleration over r. So 1r cancels, and what we have is I'm not sure how you type it. So force of tension will be equal to 10 kilograms times 0.25 meters. Don't forget, we have to use all units consistently. International system of units has to be used. Acceleration. Do we need to convert radians into degrees? No, we stick to radians because radians is correct unit divided by 2. Basically, actually, it's 200 over 8. 100 over 4, 25 newtons. All right. Theoretically, now you are absolutely ready for lab number 7. If anything goes wrong, that's not my fault. What are we going to do when a system is more complicated? When we have two objects, do I have it here? No, I have it here. Oh, I have it there. Just to increase inertia. So instead of a disk, I have another object which can rotate, and I can attach a weight to it. All right, I'm not going to use this. Next time, you can bring theatrical binoculars. What's going to happen? Oops, it's missing the pulley. So too much friction. So now the pulley almost frictionless. It's going to spin, but it's going to spin faster and faster. So we have two objects. First travels linearly, and second rotating. By the way, let's see. What's going to happen if I shift each weight away from the axis of rotation? How does it affect the inertia? It increases. More inertia, lower acceleration, so it starts spinning much slower. And this is basically one of the lab setups. One object which travels according to Newton's second law for translational motion. Second object which moves according to the Newton's second law for rotational motion. But they are coupled by the string which is A, unstretchable, and B, massless. The same string we used before many, many times. Which means all we have to do is just apply those two laws together. Skip this, skip this, skip this. Here. So we released the system from rest, and we see the weight starts moving down, slowly speeding up, and in this case, a disk starts rotating. So if we need to apply the Newton's law for translational motion, we have to show forces acting on the weight. And of course, there is only force of gravity and force of tension in the string. So that's going to be equal to 5 times 10, 50 newtons. Now, we don't know the tension, but it's there. What we know is the force of tension with exactly the same magnitude will be acting on the disk, because as we remember, string doesn't change the magnitude of tension, it only may redirect it. So technically we should use some kind of symbols to demonstrate those are actual different forces. They point differently, but they have exactly the same magnitude. The magnitude of this is equal to the magnitude of that force, so we can use the same symbol. Now, as we did this, I don't know, 2 minutes ago for the disk, the only one torque relative to actual axis is important, torque due to tension. So now we're ready to start writing equations. Well, the acceleration of the weight points down, and the angular acceleration of the disk is clockwise. Kind of makes things a little bit more complicated. And actually, we cannot neglect friction. So the disk spins clockwise, so the friction should oppose it. Torque of friction points counterclockwise. All right. Now, Newton's second law, standard Newton's second law for the object. Force of tension minus force of gravity should be equal to mass times, well, acceleration points down. A represents the magnitude of it, so done. Now, Newton's second law for rotation. Do we have any positive torque acting on this disk? Yes? Tension, friction. So torque due to friction is positive. Torque due to tension is negative, clockwise tension. Should be equal to inertia times. Acceleration also points clockwise, so according to our agreement has a negative component. Done. Now we have to start writing additional expressions which represent additional information provided to us. For example, the magnitude of torque of friction is equal to 0.1 of the torque of tension. Okay? How would we calculate torque due to tension? We know how. Force times lever arm, and the lever arm equals the radius of this disk, the shortest distance at 90 degrees from the axis to the line of action. There is one more relationship which we have to write. And we used it before once. The relationship between angular variable, specific angular variable, which describes rotational motion of this disk, and the linear variable, which describes the linear motion of this weight. First of all, because the string doesn't stretch, the distance traveled by the weight down will be equal to the distance traveled by any point on the rim, delta S rotational. But distance over time, speed, changing the speed over time, acceleration. So we had these relationships before, and we can make a conclusion in this situation that angular acceleration will be equal to, first of all, it will be equal to tangential acceleration of any point on the rim of this disk divided by the radius. But on the other hand, tangential acceleration of any point on the rim of this disk is equal to just acceleration of this weight, because the string does not stretch. What do you say? Stretched. Well, it also isn't strange. It's just a string. But so now we have everything we need to solve this problem. All important relationships are here. 1, 2, 3, 4, 5. Well, you know what to write. You can even write it. Physics is done. As long as all connections between all important variables are represented by equations, physics is done. Well, let's see how it works out mathematically. So once again, force of tension minus m times g equals, well, this is how I want to write it, and torque of friction minus torque of tension equals, and these two are related, and these two are related, and torque equals tension times radius. That is the complete system. So what can we do? Well, first of all, friction 0.1 times torque of tension, which is Ft times R, minus tension, torque of tension, Ft times R equals this. These three equations together give first relationship which we can use for tension. Force of tension will be equal to on the other hand, if I use this expression in the first equation, I don't have that unknown anymore. I still have two different variables, angular acceleration alpha and linear acceleration a, but they are related. For example, I can use this expression for angular acceleration to eliminate linear acceleration. Negative alpha 0.1 r minus r, which is, of course, negative 0.9 r minus mg equals to, where is my I is there? Yeah. And alpha r. All right. I have to stop because I have no room left. I can't write anything anymore. So what do we know in this equation? We know I because it's 1/2 mass times radius squared, and we know both. We know radius, we know mass of that weight, we know g, we know, again, mass of the weight, radius. There is only one unknown left in this equation, alpha, angular acceleration. So now you can just plug all the numbers in this equation, rearrange it algebraically, and solve for angular acceleration. After that, you can use that additional number to calculate anything you want to. For example, you can calculate the linear acceleration. If you know the linear acceleration, you can calculate force of tension. You can calculate torque. You can calculate frictional torque. Anything else after that. As long as you get one new number, you can use that extra number to answer any possible questions. If you know acceleration, where else can you calculate? Distance traveled in a certain time. You can calculate how fast it will be moving in a certain time. But for that, you would have to go back in time and use equations from the past, equations which relate variables like acceleration, velocity, time, distance, or angular acceleration, angular velocity, time, angular displacement. Okay, I think that's the answer. And and we're done for today. I'm going to pick up tomorrow from this, but you're ready to do lots of homework problems. You're ready to do the lab.
On Blackboard, I thought there's 2 spots for the Unit 6 lab on my thing. So one of them says it's blank with no grade, but the other one has my grading from the last one yesterday.
Yeah, probably one of the teaching fellows added an extra line. I'll check.
Okay.
Yeah, we don't want that.
Yeah, I think they added one because the Unit 6A put my gradient came in at the bottom, but the one that was already in by you wasn't filled.
All right. We will fix it. You will have to